So the last 2 days in class, we've discussed exponential growth and exponential decay functions. And today, what we're looking at is we're going to look at exponential growth models and exponential decay models and see how these exponential functions relate to some things that really we can apply in the real world. Okay, so exponential growth model simply looks like this. Y equals A times 1 plus R to the T. And what you need to know about this is that the A is the initial amount. Okay. The R is the interest rate. I'm sorry, I know I'm writing really small there. Doing the best I can. T is the period, okay, over which it is being compounded. Okay. The book, I believe, calls it the just give me a second here. The book calls T the time period. And finally, the 1 plus R is what is called the growth factor. Okay? The growth factor, what you're multiplying by each year. So the first example here, I know it says example 7 on my notes. It's the same as example 1 on your notes. It says you put $250 in a savings account that earns 4% annual interest compounded yearly. You do not make any deposits or withdrawals. How much will your investment be worth in 10 years? Okay, so the key thing here is it's compounded yearly. Okay, and in the time frame is 10 years. Okay, so really what you have to identify is A, R, and T. If you identify those three things, well, then you can write the equation here. So A is the initial amount. Well, the initial amount they told us we're putting in is 250. The R is the rate. Well, 4%. 4% written as a decimal is 0.04, and the time we know now is 10 years. Okay, so Y equals, now I just plug things in. Okay, A is 250, so I have 250 times 1 plus 0.04 raised to the 10th. Okay, that's my model. Or that's how I would solve this. And so finally, I plug all this in. I get 250 times 1.04 raised to the 10th. And when I plug that into my calculator, I believe I'm going to have 250 times 1.04 raised to the 10th power equals, I believe, $250 over the course of 10 years will turn into roughly $370.06. Okay, and so that's what we're looking to do here when it comes to exponential growth functions. Okay, you're growing, so you better believe that your answer should be bigger than what you started with, and so that should make sense there. Okay, again, identify your A, identify your R, and identify your T. Okay. Again, we're just going to do a couple examples of this, and then we'll look at some exponential decay examples, and we'll call it a day here. So if you feel like you have this, you may want to pause the video here and just go ahead and try the next one on your own. I apologize, I'm having some difficulties here. Hopefully this works. There we go. All right. So the next example says, you put $125 in an account that earns 2% in compounded yearly. You do not make any deposits or withdrawals. How much will your investment be worth in 5 years? Again, remember the model is Y equals A times 1 plus R raised to the T power. Okay, A, initial amount. R, interest rate. T, the amount of times that it's going to be compounded. Okay, or the time period. So the initial amount is $125 I put in. I have a 2% interest rate, and the amount of time is 5 years. And so now I just plug all of this in. So 125 times 1 plus 0.02 for 5 years. And at that point, I would just plug it into your calculator. So I have 125 times, parentheses, 1 plus 0.02, parentheses, raised to the 5th power. Hit enter, and $125, according to my calculator, is going to become roughly $138.01, and that corresponds with answer choice B. All right, so again, exponential growth, identify your initial amount, identify your interest rate, and identify the time period. Okay, I believe there's one more example here that we're going to look at with exponential growth, and then I'm going to have to go ahead and find the exponential decay example. So let's see here, see if I can get this. There we go. All right, so here we go. A business had $15,000 profit in 2003. Then the profit increased by 5.46% each year for the next 10 years. Write a function that models the profit in dollars over time. Okay, so the profit, again, start with your initial amount, right? That's your A. Your initial amount is $15,000 times 1 plus 5.46% is a decimal, 0.546 raised to the T, right, over the course of time. Well, now it says use the function to predict the profit in 2011. Okay, well, if I started in 2002 and I go to 2011, that means that my time is 8 years. And so now I take this function I already have, and I'm just going to very simply bring this down and plug in 8 for T. So 15,000 times 1.0546 raised to the 8th power. And you'll see here 15,000 times parentheses 1.0546 raised to the 8th power is going to yield $22,950 and whoops, that's a point there, not a comma, 0.56 cents. So $22,950.56 is what this investment will be in 8 years. All right, so obviously it makes sense. The more you invest, the better opportunity you have to profit from those investments over the course of time. So now we're going to go ahead and look at the exponential decay. We'll look at the exponential decay model, and you'll notice some they're very similar, okay, these two models. So the next type of model we're going to look at is the exponential decay, and you'll notice some very similar features here. A is still your initial amount. Okay, R is still your interest rate. And T is still the time period. And 1 minus R is now is no longer called the growth factor. Okay, it is now called the decay factor. So it's called the decay factor. And so there we are. Again, you'll notice the only difference is now instead of being 1 plus R, it's 1 minus R. Same concept. Okay, so again, still have to identify your A, still have to identify your R, and still have to identify your T. So Y equals, it says write a function that models the city's population since 1995. Okay, in 1995, the initial amount of people was 357,000 people. And since then, it's been decreasing by 1.5%, 1 minus 0.015 to the T power, depending on the number of years. We want to find the population in 2003. Well, again, from 95 to 2003, that's 8 years. And so I take my function and I just plug in 8 for T. So I have 357,000 times 1 minus 0.015 raised to the 8th power. And so now this model tells me that the population now is 357,000 times 1 minus 0.015 raised to the 8th power. And we're getting smaller. And so there are roughly 316,343 people left, okay, in the city. So again, exponential growth versus exponential decay is very simply there's a decay factor instead of a growth factor, and to find that decay factor, it's 1 minus the rate, okay, not 1 plus the rate as in exponential growth. All right, so the last example we're going to look at on your notes here deals with still exponential decay. Okay, this last example says we have a farmer who bought a tractor in 1999 for $30,000. The value has been decreasing at a rate of 18% per year. Write a function that models the value of the tractor over time. So again, initial value, $30,000. decay rate. 1 minus the rate, 18% is 0.18, and then T, however many years have gone by. Okay, and so now what was the value of the tractor in 2005? Well, from 99 to 05 is 6 years. And so we do 30,000 times 1 minus 0.18 raised to the 8th power. And I'm sorry, not the 8th power, the 6th power. From 99 to 05 is 6. And so that tells me the value of the tractor is now 30,000 times 1 minus 0.18 raised to the 6th power. The tractor is now worth $9,120.20. So you'll see that this tractor has depreciated in value a lot over the course of time. So again, exponential growth and exponential decay functions are seen in a variety of places in the real world, and here are just a few examples. Tomorrow we'll look at a couple more in class, and we'll go from there. Bring any questions you have as usual, and we'll see you tomorrow.